Good morning to all of you. I warmly welcome to our notable guest, Professor Sarbajit Banerjee, on day 3 of the Indo-US Webinar and the Lecture Series. Webinar we have partially concluded yesterday, and from today we will start the Lecture Series. In the whole Lecture Series, there will be the 10 special lectures. All these special lectures are based on the very core theme of the advanced functional materials, based on electrochemistry, based on energy, and our special speakers have designed their lecture so that they can start from very basic concepts and can show you or can give you the idea about the advanced problem, so that you must be aware how to start the problem, how to proceed with the problem, or how can you touch to your goals. So we are very thankful to them. I warmly welcome to all the participants who have actively attending this program, the last 2 days webinar and this lecture series. And their participation could be actually seen in this way that very relevant questions they are asking. So this shows that the attentiveness of the participants during the lecture. So today we will start our the day 1 of the lecture series, or the day 3 of the entire program. So every day we will have the 2 lectures. The one lecture will be delivered by our notable speaker, Professor Sarbajit Banerjee, and one lecture will be delivered by our another notable speaker, Professor Yuanbing Mao. So today we will have the first special lecture by Professor Sarbajit Banerjee, and every day we have fixed a program in such a way so that you cannot actually forget about the what will be the timing of the program or how we will have the lecture. So we have actually made the uniformity on all days. Our program will start at 10 o'clock. Our program will end up at 1:15. So in all days, the first lecture will start from 10 o'clock and it will go to 11:30. And then we will have the technical break of 15 minutes, and then we will start the next lecture from 11:45 to 1:15. In both the lectures, I together with our special speakers, Professor Banerjee and Professor Mao, we have actually discussed that how much time they will spend towards their scientific content and how much time they will devote towards the question answer sessions or the queries that you can raise during the listening of the lectures, and then you have the curiosity that your queries will be resolved at the end of the lecture. So that time will be 20 minutes. So the speaker will actually devote around 70 minutes in the scientific content of the lecture, and then 20 minutes for the question answer session. So with these welcome remarks, I again welcome Professor Sarbajit Banerjee for sparing his very valuable time for this long 9 days long program. As we know, sir, you are very busy. You have so many administrative responsibilities along with the academic activities. So we know your academics, and yesterday our participants were very well. They know about your administrative activities also. So, sir, with these words, I strongly welcome you. And the first special lecture will be delivered by Professor Sarbajit Banerjee. And yesterday and day before yesterday, in a very detailed, we have actually given the detailed introduction about our speakers. So today we will speak on a very basic topic of the energy, and the title of this lecture is Energy. Where are we now and where are we headed? So with these words, I request Professor Banerjee to please start this notable lecture.
Thank you, Tokeer. It is again a great pleasure to be able to speak to this audience, and thank you for sticking around. We've had a great time listening to the webinars, and thank you for staying for the remainder of the lecture series. So, like Dr. Ahmad mentioned, our plan is to really, over the course of the next 10 lectures, try to develop a pretty a comprehensive understanding of some of the materials challenges in energy and try to think about what some sort of opportunities exist, especially for students, postdocs, younger faculty that are looking to begin their research careers. I think this is a really exciting time because everything you do matters, right? We are in a once in a 200 years moment in terms of the role of science and the interplay of science and climate and energy. And there's just incredible opportunities here for the younger generation. And I say incredible opportunities, but what I also mean is incredible responsibility on the younger generations to really take up this challenge. So I thought I would spend most of today, my lecture here, trying to come up with a systems-wide analysis of energy and some of the problems then that will motivate some of the technological solutions that we need in the days and in the years to come. So one of the other sort of ideas I want to convey, and I think this will become very obvious in this talk, is that there is need for every type of science, for every type of engineering, for every type of communications. There is all of us have to sort of work together globally to tackle some of these problems that we face as a planet, right? So what is the future of energy? We are lots of issues, lots of political issues, lots of policy issues, we are facing and seeing live the consequences of global warming. So I think I'm going to start with some very elementary ideas, some formal definitions that you might see in maybe a first year chemistry or physics class. So of course, what is energy? It is the capacity formally to do work or transfer heat, right? So can you actually move an item? Can you actually increase the temperature of an item? Right. So work is the energy that is used to cause an object to move against the force. Heat is the energy that causes the temperature of an object to increase. Right. So that's a very fundamental description. This is what we're talking about, right? We are talking about being able to do work and being able to generate heat, right? And so I think where a lot of this can be broken down to is the first law of thermodynamics, that energy is conserved and it's neither destroyed nor created, and energy that is lost by a system must be gained by the surroundings, right? And this, I think this frames the rest of the discussion for us, right? So how much do we need? How much do we have, right? This is a very simple, I'm going to dive down into lots of details. And this is a very, very rough estimate, but this is a good place to start, right? So here's where we are. Somewhere over here, let me see if I can, I'm going to change this to laser pointer. Okay, here's where we are, right? And pretty soon we're going to start running into trouble as the world's sort of energy consumption increases. And then this is how much energy that we have available in the form of fossil fuels, hydropower, non-breeder efficient. And then all of this humongous amount of energy will need to be supplied by alternative sources, right? So as energy consumption goes up, this is in terms of billion barrels of oil equivalents, we're going to be running short, and we're going to have to do something about it for our future generations, right? And these are some numbers from an article by Lewis and Rosera, and also relying on some analysis in this DOE report. Okay, well, our population right now, in 2001 was 6 billion, projected to increase to 9.4 billion, and then ultimately about 10 billion, right? So our population isn't increasing as fast as it used to be. So that's a good sign, but it's nevertheless going to increase quite a bit before it stabilizes, right? The GDP is going to hopefully increase. This is a good thing. And our per capita GDP is also going to increase as more and more populations across the world come out of poverty, right? And this is of course fantastic. This is something that we have, that science is enabling, that technology is enabling more and more people across the world to come out of poverty. But this will require a greater fraction of energy, because the energy that is going to be required to meet the needs of this growing population that has a higher income is going to be substantial. So our energy intensity per person, or per year will decrease, right? But the energy consumption rate is going to massively increase, right? So here are some numbers to keep in mind, and of course there's lots of approximations here, but from 13.5 terawatts in 2001 to 27.6 terawatts in 2050 to 43 terawatts in 2100, really big. So we, by 2050, we're going to essentially need to be producing over twice the energy we were using just about 20 years ago, right? So this is a huge number in terms of how much energy that the world's going to need, right? And the carbon intensity of energy is also decreasing. Again, this is a good thing as we are in the midst of this massive energy transition, but is this good enough? Okay, so this is something we're going to have to consider. Is it good enough to save us from the catastrophic sort of aspects of climate change, right? And so we'll have to think about this. So if you think about where we're going to get this energy from, okay, so we have this massive shortfall that is looming on the horizon. We can harvest hydroelectric power, tidal power, geothermal, wind, but really the big numbers, okay, are in solar, right? Which is 120,000 terawatts of solar are incident on Earth in a year. So if you look at these numbers, 27 is a very small fraction. 43 is still a small fraction of this number. And so just to get 20 terawatts, okay, where as long as you had 10% efficient solar cells, you'd have to cover a fairly large portion of the Earth's surface, but it can be done, right? So solar has a lot of potential for meeting some of our biggest energy needs, and this is probably going to be one of the fastest growing sectors in the years to come, right? There is another source of energy that is potentially, very valuable and can compete with solar in meeting this energy shortfall, and that is nuclear. But nuclear remains controversial because we still don't know what to do with nuclear waste. There's, of course, all kinds of safety issues, even for operational nuclear plants ever since the Fukushima disaster in Japan. So many countries have disinvested from nuclear, right? So this is so nuclear, even though it's a relatively clean source of energy, is on the decline. We'll have to see if that trend reverses in the years to come, right? There is also tremendous hope, especially in the EU, in nuclear fusion. Okay, this is a big project, and if that ever takes off, if that works, it has the potential to generate humongous amounts of power. But other than that, I think we're going to be very heavily reliant on solar in the years to come. Okay, so this is a report I pulled from the U.S. Energy Information Administration as to what are the sources of energy and where do we actually end up using the energy. So if you take a look at these numbers, big source is still petroleum. Okay, so petrol, gasoline, as it's called in the U.S., or petrol as it's called in India, still about almost 36% of energy that is used in the U.S. is gasoline, right? Where does it go? Not surprisingly, 71% of this gasoline is used for transportation. 23% of it finds industrial use. Okay, and one of the things to consider as we talk about energy is of course interconnected, right? This is why energy is not just what comes into our homes or what powers our transportation, but it's also our industry. It is also sort of our the very sort of way we live our lives, right? So especially as chemists, this is an event hosted by the Department of Chemistry. Our chemical industry is extremely reliant on gasoline as its fundamental feedstock, right? So almost every organic chemical that you buy, has started its life as some sort of gasoline byproduct, or and so this is something that you can see here. 23% of all petroleum is actually going towards industrial uses, of which a lot of this is in the chemical industry, right? Okay, Then you've got 5% going towards residential commercial, and 1%, so not very much petroleum, of course, used for electricity, right? And then natural gas has been a huge story in the U.S. in the last 2 decades, and increasingly across the world. Again, not very much natural gas used for transportation, mostly for industry, residential, commercial heating, and then for electric power. So natural gas plays a big role in power generation. Coal, again, the most biggest consumption of coal is simply for direct generation of electricity in these peaker plants and coal burning plants, 92%, right? And in India, in China, still heavily reliant on coal, which is one of the most toxic fuels out there in terms of the emissions, right? So there's no alternative unless solar takes off, unless renewable energy takes off. Coal is here to stay, and but this is, I think, something that is changing very rapidly. Okay, so renewable energy relatively small in 2011. This is a number that I'm going to show you is increasing a little bit, going towards transportation, and again a good mix. Some of it going to industrial uses, and then about 54% going towards electric power generation. Nuclear power, of course, almost entirely to power the grid, 100%, right? So complex web with lots of different energy sources and sources of consumption. So this is something to keep in mind. If I advance 6 years, 2017, not a whole lot has changed, except natural gas is up. Coal is substantially down from 20% here to 14%, and renewable energy, again, slightly up. But as I'll show you, the energy transition, the transition to renewable energy has been slow, and perhaps by some predictions will continue to be quite slow in the years to come. So let's break this down a little bit. Let's talk about this part of the grid, the segment here, electric power generation, mostly the electric grid. On my first talk, I discussed this a little bit, but this is something that obviously affects all of us, and we talked about this. The grid is, in a sense, this is a quote from the Atlantic Monthly. It gives us freedom. Having power in our homes, having power in our offices gives us freedom from darkness, freedom from cold or heat, freedom from boredom, and the freedom for me to sit thousands of miles away and talk to you, right? This is all enabled by the grid. But again, this comes at a cost of millions of metric tons of CO2, right? So let's think about grid here. Where is this energy coming from? Again, not gasoline, not petrol. This is more petrol is mostly going towards transportation. A lot of energy coming from natural gas, a big chunk from coal, some from renewable energy, and some from nuclear power, right? So it's a pretty big mix here. And then the grid today is still very much reliant on fossil fuels, on coal and on natural gas, and relatively less so on renewable power like windmills and such. So this is again a quick recap. 2011, natural gas, electricity sources 24.8%. Then we've got nuclear about 20%. Hydroelectric is large of the renewables. Coal, 2011 was very big, about 40%. It's smaller now, right? So coal. So how do you actually convert coal, natural gas, and petroleum to electricity, right? So this is a stylized schematic of a coal-fired plant. This is a chemical reaction for what happens there. So essentially, you burn coal, you combust coal, right? This is an exothermic reaction. So you burn coal, you generate carbon dioxide, you release that comes right out of the stacks here, along with a whole bunch of other toxic materials. So coal, of course, is something that is a natural resource. You take it out of the ground, but it's not pure carbon. It is a lot of it is pure carbon, but it also has, just being that it's a fossil fuel source, it has sources of sulfur, it has sources of nitrogen. which gives rise to SOx emissions, NOx emissions, often things like mercury emissions, some of which are mitigated at the stack, some of which are not adequately mitigated and are emitted out into the environment. So you burn carbon, you generate carbon dioxide, and it's an exothermic reaction, so you generate a bunch of heat. You take the heat and you use that to essentially boil water, right, in a boiler. And that boiled water, the steam that you generate, the steam moves a turbine, and the turbine results in power generation, right? And so really what we're doing is running a gigantic kettle by burning coal, right? To boil water and to move a turbine, right? So it's not very efficient in many of these processes. Combustion is not very efficient. The boiling of water has inefficiencies, and then of course the catastrophic consequences of emitting all this carbon is pretty obvious, right? And then similar idea with natural gas, methane as an example. You burn methane and you generate CO2 and water and heat, and again use that heat to run boilers and essentially run a turbine, and that allows you to generate power. Again, you emit carbon dioxide and water vapor out into the environment. So point one, essentially you can see here the production of electricity generates carbon dioxide, right? So this is a major problem. If you consider then transportation, okay, again transportation, if you take a look at this part of this picture here, most of the energy for transportation is coming from petroleum. Some of it is coming from natural gas, and then only a minor fraction in 2017 coming from renewable energy, about 5%, right? So very, very heavily dependent on petroleum as our means of mobility, right? And this is true for cars, this is true for airplanes, this is true for ships, right? So we're extensively dependent on gasoline, on petrol to run this. And again, the reaction there, the fuel, essentially hydrocarbons, right? Hydrocarbons that we combust using oxygen to generate CO2 and water. So one more point to keep in mind, just sort of amplifying the previous point, is that internal combustion engines also will generate CO2, right? And so this is the challenge here. Most of this again coming from petrol, right? So historically in the U.S., what has happened, and this is something to keep in mind, why one of the questions, if you go back and look at the literature 15 years ago, 20 years ago, people were predicting a much sharper sort of acceleration of the green energy transition. It's been slower because it's a moving target, right? So just as one of the things to keep in mind is fracking and enhanced oil recovery methods have made extraction of petroleum much more easier. So where it worldwide projected reserves of accessible petroleum have really dramatically increased, and so there is a boom in the production of oil that has happened in the last couple of decades, especially in Texas, in West Texas, in the Permian Basin, and in North Dakota, where these cost-effective drilling and production technologies have really led to this massive resurgence of petroleum production, right? So there's and this is actually renewed sort of the idea of energy independence in the U.S. And so typically refineries in the U.S. are dealing with about 18 million barrels a day, so humongous amounts of oil. 11 million barrels is domestic production, 7 million barrels coming from abroad, mostly Mexico, but very large part from Canada, okay, from the oil sands, heavy oil sands in Canada. The three biggest sources of exporters of oil are, of course, or in terms of reserves of oil, are Canada, Venezuela, and Saudi Arabia, and these have some of the largest deposits. But again, one thing to keep in mind from a perspective, a lot as we sort of exhaust our sources of crude oil, of light crude oil, we're moving more and more into heavy crude and unconventional deposits, and and they can yield reasonable quality oil, but oftentimes the processing that goes into it is quite a lot more energy intensive to produce the same amount of oil. And then also they typically have very high sulfur content. So again, lots of processing required, and danger of contamination of SOx emissions and such, right? So okay, so light sweet feedstock, we're still doing okay. This is Saudi crude, this is West Texas crude, and it can be handled relatively easily. But then more and more, there's a reliance on heavy sour crude coming from Canada and from Venezuela, which requires much more complicated refineries. But I also want you to think about this for a second. It's not just these systems are extremely complex in their interconnections. So look at all of the products that come out of a refinery, right? So on the one hand, you've got gasoline. This is what most of you use every day, whether you drive to work, or you drive a motorcycle, or you get on a bus. You're typically burning gasoline. But then there's also liquefied petroleum gas that you might be using for cooking, naphtha, and both of these are huge precursors for the entire chemical industry, right? So our plastics industry, all of these are heavily reliant on these lighter fractions providing precursors. Then you've got diesel, jet fuel, fuel oil, which is often used in ships, so lower quality, and then the residues, right? And then asphalt is used for making roads and for making essentially as a vital component of infrastructure. So when we talk about energy, when we talk about petroleum, we're not just talking about gasoline and electric vehicles, but also our chemical industry, also our infrastructure industry, right? So when we talk about this whole world out here and a transition that is coming, this is the transition that will profoundly affect not just our energy needs, but also every possible industry will be affected by this. So why are we so addicted to gasoline? Okay, there's some really easy science that you can talk about. This is chemical energy density, right? So how much energy is stored per kilogram in the bonds of gasoline? How much energy is stored per liter volumetrically in these different fuels, right? So we talked about hydrogen as a fuel. I talked about hydrogen as a fuel on the first day, and that's what Dr. Ahmad also works on in thinking about photocatalysis and understanding solar fuel production. But let's compare gasoline and diesel to hydrogen, right? So gasoline and hydrogen in specific energy in millijoules per kilogram is very high because hydrogen is very lightweight, right? But where it doesn't do so well is in terms of millijoules per liter, right? So the volumetric energy density is just amazing for and really unprecedented for these fossil fuels. And this is what allows you to have a relatively compact gas tank or petrol tank and in your car that can take you hundreds of kilometers, right? Thousands of kilometers with relatively little fuel powering this through, right? And so where things like hydrogen are very light, they require a lot more volume. So this you can see this for a comparison to different fuels. So the chemical energy density is really been difficult to overcome. And I want to show you another example here, right? And I have there's just several versions of the same exact plot, and you can see where diesel and petrol is here. And then you look at lithium-ion batteries as a comparison. Okay, also much less effective in terms of how much energy you can store per weight, how much energy you can store per volume, right? So very much, you can see why, gasoline has maintained the predominant position for so many years. It's got fundamentally some incredibly good properties in terms of chemical energy density. And what that means is we talked about this on day one. The fundamental idea of storing energy in the form of chemical bonds. Well, gasoline is a very effective way of doing so, particularly from the perspective of volume, right? And so replacing it really requires a lot of work, right? A lot of work in terms of storage, a lot of work in terms of everything else. So energy density, the cost, the weight, and size of onboard energy storage are really important characteristics of fuels for transportation. Fuels that require large, heavy, or expensive storage can really reduce the space available to convey people or freight, and really makes it difficult to operate a vehicle less efficiently, or can make it too costly, even if you take into account cheaper fuel. So if you're going to end up taking a lot of space just storing the fuel that's going to move you forward, and so that you can't actually carry enough people, carry enough freight, then makes that whole thing much more inefficient. So compared to gasoline and diesel or petrol, other options may have more energy density per unit weight, but none of them are really competitive in energy per unit volume, which requires an entire redesign of how cars work, how transportation works, right? Another plot showing you much the same information, and you can sort of see this here. When compared to gasoline and diesel here, everything below this is heavier, everything above this is lighter, right? And so on this plot, you can see that batteries or methanol or ethanol tend to be heavier than in terms of energy content per unit weight. So they're not great. And then over here, energy content per unit volume, right, is for something like liquid hydrogen or compressed hydrogen gas much lesser than gasoline, which means that it requires much more storage space if you're going to use this, right? And if you look at again, if we do a direct comparison for hydrogen versus gasoline, again, much lighter in weight. This is a good thing. Cooled liquid hydrogen, much lighter in weight, but requires a whole lot more storage space, right? So if it's a gas, especially a lot, we can cool it down and store it as a liquid. It requires relatively less, but this is a problem, right? The sheer volume of required. And in terms of battery types, okay, batteries are not very efficient either in mass, or in volume. And this has been an abiding challenge for electric vehicles, is that most electric vehicles right now are essentially just big batteries on wheels, right? And this makes it quite challenging because it increases, of course, the size of a car. So we talked about two problems, right? Just going back, production of electricity generates CO2. Internal combustion engines generate CO2. Is CO2 a problem? Well, I think we know it is. So CO2 observations at the Mauna Loa Observatory in Hawaii, it goes back to the 1850s, and we've seen this huge increase, right, from 290 ppm to about about 380 ppm now, and this number has been quite scary. These are independent measurements at the Scripps Institution of Oceanography Observatory, and we know that the amount of CO2 in the atmosphere is correlated with temperature, and this has led to this huge quandary that we find ourselves in right now. So essentially, our current energy consumption strategies are not sustainable, and we need alternative carbon neutral energy sources, right? So, and this is really, if you think about the magnitude of this problem, this is so huge, right? It's such a huge problem. I talked about, we are going to need to double by 2050, which is not that far away. 2050 is, I would think, in our lifetime, certainly in the lifetimes of the students attending this seminar, right? We're going to have to come up with double the amount of energy that we need today. And then we're going to have to come up with double the amount of energy while, dramatically reducing our carbon footprint while dealing with a larger population, a substantially larger population, and a population that has greater needs. So there's a lot of changes coming in the next 2 decades, 3 decades it's going to be a very critical time, but really we're going to need a lot of sort of scientists on board to solve these challenges. So here's where we are, right, in terms of CO2 emissions. This is sort of 2020, and we've had over 1 degree C rise in temperature, and you can see the prediction here by as the CO2 emissions keep increasing, the different scenarios, we're going to have up to a 4, maybe 5 degree C rise in temperature by maybe a 4.5 degree C rise in temperature by 2100. So this is a scenario of unmitigated growth where nobody cares and does nothing. We're going to end up with 4.5 degree C rise. This is going to be catastrophic across the climate, right? Across the planet, 4.5 degree C rise will mean melting of large amounts of polar ice caps and rising sea levels and natural disasters across the world, right? A little bit of a more moderate scenario right here. And then as you sort of think about some more mitigated scenarios, this is the ambition of the Paris Climate Agreement, can we keep emissions below 2 degrees C? Can we, or at least below 1.5 degrees C, right? And again, just to also keep in mind, we always talk about CO2, but it's not just CO2. Methane is also incredibly dangerous as a greenhouse emissions, and NOx, and as well as SOx and hydrofluorocarbons and so on and so forth are also major contributors. So global warming, like I showed you a couple of slides ago, depending on the choices we make now, they will determine what happens in the next 20 years, the next 50 years, the next 100 years. Are we going to have 4 degrees C, 5 degrees C rises in temperature? So in Paris, we had this historical agreement that basically said that we're going to limit the temperature rise to 1.5 degrees C. And this is a very ambitious agreement, but this is going to require an incredible amount of new science and technology and concerted action by policymakers across the world, right? And so this is a slide I got from Dr. Julia King, who is on the UK's climate change committee, and she's plotted different scenarios here. So if we go with business as usual, hopefully by 2060, 2070, people will finally start to mitigate greenhouse emissions, but it's going to be too late in the sense that we're going to have a very significant rise in our CO2 emissions, and the overall emissions that have accumulated. So we are going to stay below 2 degrees C. We're going to very soon, so this is 2020 right here, right? We're going to very soon have to sharply curtail CO2 emissions, sharply curtail other greenhouse gas emissions. And at some point, perhaps at the end of this decade, we're going to have to start to do something about carbon emissions that is not just cutting down on carbon emissions, but actually doing negative emissions, right? So somehow taking the carbon out of the air and storing it in some shape or form, either in our built environment or inside, old mines or something like that will have to be done, or in our trees. So we're going to have to potentially remove 20 gigatons per annum of carbon per year, which is going to be, if Dr. King has done the math here, okay, if you assume an average carbon price of $200 per ton, this is going to be a $2 trillion per annum industry in the years to come, right? So we're going to remove 700 gigatons of carbon cumulatively. It's going to cost about $140 trillion. So our U.S. economy, the size of the entire U.S. economy, is 21 trillion. So about 10% of the size of the economy is the cost of taking carbon out. So this is, you can think about this as this incredible task that you have in front of you, the generations have in front of you, but also an entirely new industry that doesn't exist right now that is going to be needed, the idea of taking carbon out of our atmosphere. Right. So this is a slide again from Dr. King showing some of the International Planet for Climate Change model pathways. How do we stay below 1.5 degrees C, right? Increased temperature rise. So you can see a scenario here where, there's 4 different scenarios, and depending on the scenario, we're going to have to remove more and more gigatons of carbon dioxide from the atmosphere, carbon from the atmosphere, right? So you can see the first scenario, if you're extremely aggressive now, right away, where social, business, technological innovations push reduced energy demand by 2050, and by downsizing our energy system, by really having a very aggressive energy transition, we can sort of do this mostly by just afforestation and land use, okay? And this afforestation is the only carbon dioxide removal option, and we are without directly needing carbon capture and storage, right? So this is possible, but our time's running out. This is going to need very aggressive, concerted worldwide action. I think it's pretty safe to assume that this is not going to happen, because the world where it is now, especially post COVID-19, with all of the economies in disarray, there is not a whole lot of interest across the world in this sort of a sharp transition, right? Well, which then brings us to scenario 2, where we've got a broader focus in sustainability, but a relatively slower decline in carbon consumption. But this scenario, so we're going to move towards sustainable, healthy consumption patterns, have low carbon technology innovations and well-managed land systems. But then we're going to have some bioenergy and carbon capture and storage. We're going to have some sort of negative emissions there associated. Again, $70 trillion worth, about 348 gigatons worth of carbon removal. And a middle of the road scenario where we have generally historical patterns, and we fundamentally have emissions reductions mainly achieved by changing the way in which energy and products are produced. We can go with this, and honestly, this in the absence of concerted action, this seems to be sort of where we are headed. But we're going to have to somehow then, as time goes by later in the century, really take out a lot of carbon, do a lot of carbon storage, and this is going to be very aggressive. And then the last scenario, and I hope we don't go here, but it's again quite possible, a resource and energy intensive scenario where we continue to have economic growth and globalization, where we have these incredibly greenhouse gas intensive lifestyles, where our transportation fuels continue to be mostly petroleum, and livestock products continue to produce methane, and we're going to basically have we're going to have to rely very extensively on carbon capture. We're going to somehow have to take carbon out of the atmosphere. So this is going to be a really important thing. So okay, so let me talk about this again from a big picture perspective. This is how much energy we're going to need, thinking about different scenarios by 2100, right? So you take a look at this. This is we're going to have a pretty large increase in energy as our populations increase, as the standard of living increases, and we're going to have to somehow meet this shortfall. But then at the same time, we're going to have to address carbon, which is ultimately going to involve dealing with carbon emissions. And so we have to, as a society, as scientists, we're going to have to converge on some sort of medium where we mitigate the use of carbon intensive sources, and then to the extent that we cannot get rid of carbon intensive sources, we have to have negative emissions technologies, as well as things like afforestation and land use that counteract these effects and can capture some of this carbon back. So a difficult problem, the challenge of a lifetime, the challenge of a generation to take these on, and this is going to be, again, the last 2 years have seen an incredible amount of science as the world has tackled COVID. This is going to be something that's going to be again, it's going to require global effort, bringing together the best minds across the world. So Think of this talk as a call to action for all of the young scientists that are looking to make a difference. Never has there been, hopefully these two simple graphs show you the magnitude, the immense magnitude of the problem that we face. How do we meet the energy needs of our growing populations, especially in emerging economies like India, where very large sections of populations are coming out of poverty? How do you meet their aspirations? We're going to need to produce a lot of energy, and how do you do it without our conventional routes? How do you do it while sort of avoiding climate change? This is going to be a huge issue. So moving along to the idea of electromobility, and this is a graphic I stole from Siemens. Okay, so electromobility is something that we're going to also have to greatly focus on. So one idea is that folks have been working on are electric vehicles, and again, electric vehicles are not free, right? So electric vehicles essentially are replacing gasoline with electricity, but electric vehicles intrinsically will not be incredibly clean until the grid has become clean, right? But so this is something to keep in mind. Electric vehicles as a percentage of total vehicle sales. So countries like Norway doing very well, but in the United States still very low, less than 2%. China is still quite low, 4%, right? So and if you sort of take a look at this, this is from Deloitte, the annual outlook for global passenger car vehicles, so global battery electric vehicles are going to increase, but there's still a relatively small portion of the market share, even all the way up into 2030. So this is something that has greatly accelerated, and we'll talk about this in a few seconds. But again, still lots of progress to be made. All right, so if you take a look at this as a percentage of the market share, the US EV market share, even by 2030, is still a relatively lower number. Again, this is the global number here, about 30%. Okay, so which means that the number of cars are increasing. Even though this increases, this still means that a very large predominant majority of cars by 2030 are still petroleum, guzzling, gasoline-driven powered vehicles, right? So there's still lots of work to be done to accelerate these slopes to make sure that they go higher. And you can sort of see this in some senses, what is going on here. Look at China. China is making a sustained, concerted effort to really get on top of this, and they're promising by 2030 to have 50% transition to electric vehicles, and by some indications they might do this sooner. They might there's some indications of an even more aggressive trajectory in this direction. The EU has been also quite aggressive, but again, still lots to be done here. So what's going to end up happening? These are some projections again from the Energy Information Administration. Gasoline consumption will decrease, okay, substantially for light duty vehicles, especially for passenger vehicles. So this will happen, but then ultimately there is a point where we'll start to sort of go back again as more cars are on the road and such. So this is something to keep in mind. All right, so right here again, so predictions for energy consumption. One direct area where people are making a lot of progress, electric vehicles. So transportation is going to decrease, at least in the near term. Again, electric power, as things get, we have this shift towards renewable energy, we're going to see at least a slight dip, but industrial power energy consumption will increase. And so again, if you take a look at biofuel, the big stories here, huge reduction in coal across the world, and hopefully this is going to be true in India as well. India is still very highly reliant on coal, but a big reduction in coal. because there's just, it's much worse than even natural gas. Natural gas is massively increasing because of these new drilling methods, these new fracking methods that are making available a lot of cheap natural gas. Petroleum will slightly decrease at least, and then you've got something like renewable energy massively taking off, and this is good news. But also, if you look at the slope, by 2050, still only about, still relatively small. So still lots of work to do, right? So what factors are driving increased adoption of electric vehicles? Well, one, changing customer sentiment. Again, this is something I took out of Deloitte's report. They've done a very extensive study. Policy and legislation, in particular, things that are happening across the world. And again, one of the things to keep in mind, in science we like to work in the lab, but we are increasingly living in a knowledge-driven economy where the science we do in the lab has really widespread ramifications for all of public policy, and so some of what we're starting to see across the world is much greater fuel economy and emissions targets. So these are California has been a leader, the EU has been a leader in really pushing the auto industry to adopt to these targets, to reduce emissions, to have fuel economy. What you've seen in cities across Europe now are citywide access restrictions, basically saying if you drive a gasoline-driven vehicle, then you're going to have to pay more to access city centers, and then financial incentives, direct financial incentives, essentially giving rebates and such to those that buy electric vehicles, because the price of electric vehicles continues to be a major challenge, right? And so another thing that is happening, and I'll talk about it in a second, is a big push from equipment manufacturers to really retool their corporate plans, and then the role of corporate customers. A lot of cars are bought by individuals, but companies buy a lot of cars, and a lot of them are increasingly saying, look, we're going to, as a company, move towards electric vehicles. These are some of the biggest drivers for increased adoption, and you sort of see some of these big events that have been happening this year or the last few years, right? We are in the midst of a massive transition. So, over here, I'm just going to quote a few things. Honda recently announced that all European mainstream models will be electric vehicles by 2022. That's literally next year, right? Every vehicle they sell in Europe will be electric, right? And Volvo, for instance, 1 million total EV sales by 2025, which will be 50% of all global sales. So there's these big changes coming. Again, Honda here basically says that about 2/3 of their sales by 2030 will be global electric vehicles. The majority of the sales will be global, globally will be electric vehicles. So a really big transition coming down the pipeline here, and this is going to especially change the face of the transportation sector and what it looks like. So again, what's holding it back? One of the biggest challenges holding it back is driving range. So range anxiety is very real. This is a very across the world, is how much we are all used to driving cars where you run out of gas, you go to a gas station and you charge it. The lack of an infrastructure, the lack of charging infrastructure, and then how far you're going to be able to drive it. So these 2 points are really connected. Is a major problem across the world in acceptance of EV. The cost is very high, and a lot of these, ultimately, the driving range, the vehicle charging infrastructure, the cost, all of these are fundamentally related to one scientific problem, which is the battery, right? So, and then the other concern, as you can see here, safety concerns with batteries, right? So ultimately, what is holding up EV adoption across the world is fundamentally our challenges with electrochemical energy storage technology. So this is an example of where very fundamental discoveries in science are rapidly finding use in technology and then changing our world, right? So this is, again, a message to students to really think deeply and get involved, So the grid of the future we're headed to. So lots of exciting stuff happening in electric vehicle space, in transportation space, but lots more to be done. If you think about the grid of the future here, we're moving towards a much more distributed grid, lots of solar panels in this figure, distributed production, storage. And so what's going to happen all the way, again, projections up to 2050, as you've already seen, coal is on a sharp decline. And it's because it's one of the dirtiest fuels out there, not just in terms of the inefficiencies in combustion, but also in terms of all of the other pollutants that are emitted. Nuclear is relatively clean technology, but really just hurt very hard by a Fukushima disaster, and number two, our inability to have a long-term solution to nuclear waste anywhere. Where do we store this waste? What do we do with it? This remains a humongous problem. And then renewables rapidly rising, but still only about 30%, perhaps even a little bit less. This is in the US, globally perhaps a little bit less. And and natural gas continuing its rise as fracking technologies make available this fuel, right? And within the renewables, like I talked about, the big winner, or has to be the biggest rise, is going to be solar PV. And then you've got, hydroelectric already fairly saturated. There's only so much you can do here, and then some increase in wind from where we are right now, and geothermal. And another point I want to make, we are also going to see a big shift in the chemical industry. As gasoline production changes, again, moving much more towards also natural gas products in the chemical industry. So big changes in the grid, but again, major thing to worry about is carbon dioxide, right? So I showed something similar on my seminar a couple of days ago on day one. So with the last 4 years, the cost of solar panels has dropped tremendously by almost 50%. And we're powering about 12 million homes in the US with solar. But there's cloudy days, and wind again is we've had a massive increase in wind capacity, 400%. But again, there's still days, so we're going to have storage coupled to solar, coupled to wind to better utilize these technologies. This is kind of an interesting trend. I just want to talk about Germany. Germany's been a real pioneer in making the energy transition extremely well planned, and the hope is that they will completely phase out by 2040 all coal power, all nuclear power, and really move to renewables and perhaps ultimately the fusion as a means of providing global their energy needs. A couple of concepts that are somewhat market-based that I want to introduce. One idea is the levelized cost of energy, which measures, what is the cost of energy over the period of the lifetime of the plant. And the reason you sort of need this is when you're comparing all sorts of different fuels, all sorts of different energy technologies across different types. It's important to put them on the same scale. So this is from the DOE. And so if you kind of think about this and say, well, for a power plant, it's about $100 an hour, the initial costs and financing. The annual expenses are $25 an hour. So then the annual cost per hour per year is $125. It produces 1,000 kilowatt hours. So we basically say our LCOE, the levelized cost of electricity, is $125 per 1,000 kilowatt hour per megawatt hour, right? So the LCOE is an important metric. It is the installed capital cost, the operating cost, converted to a level stream over the entire financial lifetime. And this is really important because a lot of times you might have one energy generation technology that's going to be 5 years, another one that's going to be 20 years, and so putting them on an annualized basis is really important, right? And then also thinking about what is the cost that you have to pay upfront. A lot of the renewable energy technologies require an initial investment, but then not as much recurring costs. But then the other thing to also think about is the levelized avoided cost of electricity, which basically reflects the cost that would be incurred to provide the electricity displaced by a new generation project. So if this project did not exist, what would you have to do to come up with the power that is needed? So that's the levelized avoided cost of electricity, right? And so power plants are considered based on comparing these two values, the levelized cost of electricity and the levelized avoided cost of electricity. And you sort of see this here. Right here is economically unattractive. On this top quadrant here is economically attractive. And so the only things that are really economically attractive are solar power and perhaps this advanced combined cycle for natural gas. Pretty much all of the other technologies, especially coal and nuclear, not so much, right? And so we kind of look at this for the U.S. Solar PV's economic competitiveness is relatively high, all the way because of tax credits, and so and also the declining costs of solar. So basically, solar PV is going to remain economically competitive across the country, and because solar PV provides electricity during the middle of the day, when you really need electricity, and when electricity prices are relatively high, the value of photovoltaics to the grid is really high. So when you basically think about what would you need to replace the solar plant, and in calculating the levelized avoided cost of electricity, the price of replacing the solar is quite high. So solar is very often the best alternative, because it's giving you power in the middle of the day when you need it the most. So natural gas combined cycle is high for now, and this is not the best news for renewable energy, but it's not going to be something that lasts for a long time, because ultimately the prices will increase for natural gas as we start running out of this resource. So if you take a look at this, these are 2019 numbers just from 2 years ago. The bottom side here of the graph are retirements, and the top are installations, all the way up to 2050. So what you're seeing here, a lot of retirements of coal, oil and gas, and then new capacity coming online. Lots of yellows here, lots of solar, lots of wind, and still oil and gas, but almost no nuclear. Nuclear is mostly kind of declining in the years to come. Okay. All right. So solar cells, what do they do? How do they work? Silicon and beyond. So solar cells convert. What do they do? Well, they convert solar power to electric power, right? Electrical energy. That's the idea. So the basic requirements for solar to electrical energy conversion: you want to have light absorption, right? So something's going to have to absorb the light. That something is usually a semiconductor. Separate the electron and the hole. So you excite an electron over here, and you have the hole here, and essentially the electron moves through an external load, and you generate a current, right? And it recombines with the hole, right? And you repeat the process all over again, right? So this is the idea. And you can have an interface that's either a PN junction or a bulk heterojunction or dye sensitized solar cell. And then the current times the potential difference gives you the power that is generated. Okay, so this is a very simple description. So the heart of the silicon solar cell is absorption of light to generate charges, and then and what you want to do is to keep those charges separated and to flow them through an external circuit, right, to generate electrical energy, right? So this is a PN junction solar cell, perhaps the most common technology out there right now. So you have light exciting, so creating an exciton, and then you've got to deplete. So at the depletion region between P-type silicon and N-type silicon, the electrons will flow once you've excited an electron from the valence band to the conduction band. The electrons are going to flow through the N-type region, which is the region where they are much more conductive and in abundance, out through the front contact and through a load, the holes are going to flow through the p-type, and they will be combined with these electrons coming right through at the back contact, right? So this is the fundamental idea of a silicon solar cell, still the most abundant type of solar cell. And so exceptionally efficient power, the power efficiency of a solar cell, right, is fundamentally defined by how much power is produced as a function of how much light is incident on it, right? So it's a pretty simple metric. How much electricity do you get for the number of photons that are produced, that are sort of incident on it? And you can generally get that as a function of the voltage, the open circuit voltage, the current that's flowed through it, so voltage times current times a fill factor, which is a factor that reflects the shape of this curve, right? So essentially, when you've got a short circuit, when your voltage is 0, right, you have a lot of current, right, but you're not generating a lot of power, or at the point where you have you know, an open circuit, the opposite of short circuit, you don't have any current, but you've got a very high potential, right? So you want to operate somewhere in this regime, and this gives you the overall power, which in this case is you know, for a good silicon solar cell is 22.5%. So Dr. Didi Sarma showed a graph very much like this. This is a compendium of the performance of solar cells that's compiled by the National Renewable Energy Lab in Golden, Colorado, where you can see, and these are benchmark solar cells over the years, big trend upwards. You can see this for silicon, for different quantum dot solar cells, and what he pointed out was really amazing. This work on perovskite solar cells, right? So then the question is, why isn't the world covered with silicon solar cells? Why don't we just have solar cells everywhere? You know, we could have thousands of solar cells. Well, what it comes down to is this sort of trade-off between efficiency on the one hand and cost, okay, on the other hand. So generation 1, crystalline silicon, like the one I showed you, having a PN junction, essentially tends to be relatively high in cost. The cost has been decreasing, tremendously decreasing, thanks again to innovations in China and really large subsidies that have been available across the world. So polycrystalline silicon has been decreasing, but still relatively high. And this has to do with the fundamental nature of the technology. It requires 99.9999% pure silicon. And then the other challenge that I'm going to talk about in a few moments is the efficiency of single junction silicon solar cells is also limited, or we're sort of hitting that limit. It's limited by the Shroppi-Kaiser limit, and it's sort of generally in this range. So if you ask yourself the question, why don't we have a world full of solar cells? It's primarily you know, limited by this combination of the efficiency we get times the cost that we have to pay for it, right? Generation 2, again, Dr. Sarma, Didi Sarma, introduced this idea, so I'm not going to go too much into detail about this. These are dye-sensitized solar cells, or amorphous silicon, or quantum dot, or like these organic PVs. They tend to be relatively lower in terms of the efficiency, but typically much better in terms of cost. But well, again, why is it that we don't end up covering the world in these cheap, low-performance solar cells? And I'm going to come to this again. The challenge is it's not just the solar cell; it's everything around it that has a certain cost. And that even if you make the solar cell incredibly cheap, the balance of systems cost associated with it, that's not going to come down below a certain value. So again, this is a practical limit that you're hitting that's shown in this blue line, is you're not going to come down below the cost. Your efficiency is still sort of low. So really, where we would like to be is Gen 3 right here, where you get very high efficiencies and you're still much lower cost, ideally even pushing lower below the BOS idea. So okay, this is something to think about. It's a charge separation. So we talked about dye-sensitized solar cell. This is a simple idea introduced by Michael Gretzel. Use Gretzel type solar cells. Again, you excite a dye, and then you get the electron to sort of move through, and you end up regenerating the whole here using a iodide triiodide couple. And again, the electron moves through. So this is not as efficient, but it can get pretty good, and they're relatively low cost. Right? People use titanium dioxide along with these dye molecules, and you can get a really good combination. So inexpensive materials and high interfacial area to promote separation of charges. So the original configuration of this are really basically nanocrystalline TiO2 with different sensitizers. Okay, and this is again some of the best dye-sensitized solar cells measured at NREL. We have about a 10% efficiency, so substantially lower than silicon. But again, what is makes up for it is the price. Okay, so again, the challenge though, right, is that even if you really made the solar cell so very inexpensive, I have on the right hand side here all of the other things that have to go in. You have to have wiring, you have to have switches, you have to have mounting systems, inverters, power conditioners, just this massive set of needs that are required that we cannot go below, right? And this is so ultimately we're limited by this. Even if we have very low cost solar cell materials, you still have to have this balance of systems cost, and so this is limited how much solar cell penetration there has been, right? So again, there's some other fundamental science issues we're still resolving. This is the Shockley-Kaiser limit, which limits the efficiency of solar cells. And so essentially, what happens is if you end up, this is silicon. The band gap is 1.1 eV or 1125 nanometers, right? So right here, and so what ends up happening is you excite with higher energy, right? In the visible spectrum, the electrons and the holes decay to the conduction band edge and the valence band edge. So all of this energy that was absorbed is effectively lost, right? So you're only going to get back because you're going to generally capture the electron from here, and it's going to make its way to the circuit. You end up losing this part of this energy, and this is the fundamental challenge with silicon solar cells or single junction cells, is this Shockley-Kaiser limit, which then limits the maximum achievable efficiency. There are, again, it's very exciting new work about how do you avoid these efficiency losses, and that has to do with, could you use a combination of different materials that are tuned to the solar spectrum? Could you have some that are high, some that are medium, some that are low, and you line them up so that photons that make their way through with different wavelength selectivity. Okay, so this is incredibly useful. So this allows you effectively to go beyond the Shockley-Kaiser limit. The other idea that people are quite excited about is the idea of hot carrier extraction. So instead of letting thermalization happen, can you get these carriers out while they're hot and get this entire spectrum instead of letting them relax? And then the other idea that lots of folks are working on is the idea of multi-exciton generation. So you excite high and you do get thermalization, but can you generate more than one electron? Can you sort of start these knockout Auger processes and such that give you multiple electrons, and that will be so for one photon you end up getting two or more electrons. So those are some goals those are some ideas to sort of go beyond this Shockley-Kaiser limit that I'm sketching here into this regime of higher efficiencies, and then also hopefully pushing down in cost meanwhile. So this is something to keep in mind. This is the next generation. You heard about perovskite halides, tandem solar cells, up and down conversion, quantum dot based cells like the perovskite halides, and you can sort of see this here, massive increase in the perovskite halides over the last this last decade. Okay, so I will just take 3 or 4 minutes just to now finish up. One of the challenges with solar and with wind is, of course, and I showed this graph the other day, the capacity factor, which measures how often a plant is running. A power plant with a capacity factor of 100% means it's doing very well. But this is quite low for solar, right? Because the sun is only shining for a few hours, and so that this essentially means that we're going to need energy storage, lots and lots of energy storage. There's lots of different options for energy storage. And it, again, you can sort of classify it based on how much energy you want to store, and then how quickly do you want to discharge it back. So, for example, a flywheel stores relatively small amounts of energy, but you can very rapidly get it back. Batteries can store more, and you can get it back reasonably quickly. And on the other hand, you've got something like pumped hydro or hydrogen, where you can store a lot of energy, but relatively slow in discharging. So another version of this figure, energy storage. Okay, we generate a lot of energy using solar and wind. What do you actually want to do with it, right? In terms of storage, do you want to just use it for uninterrupted power supply? That's what UPS means. So essentially, just for short bursts. So supercapacitors can do that. Flywheels can do it, especially high energy supercapacitors, all kinds of batteries. You want to use it for load leveling, so shifting the load. Lots of opportunities here. And as you go into relatively large amounts of energy that you don't have to get back that quickly, then these redox flow batteries especially good. And then at the very high end for bulk power management, pumped hydro, compressed air energy storage are good. Most of the energy storage, at least the grid level right now in the US, is pumped hydro. So essentially what that means is we use the energy to move water uphill and then let that come down when we need it. For the other 6%, it's sort of a mix between battery and thermal storage, right? So this is to keep in mind. And again, it's not just energy storage. We're also going to have to think a lot about carbon storage. So this is going to be important. And I have 2 lectures coming up. I'm going to skip this for now. But okay, so as the energy transition accelerates, we are in the midst of a millennial change in energy patterns, which is going to have profound consequences for industry and and our way of life. And there's really what we have to think about is how do we accelerate the energy transition through advances in energy conversion and storage, and then energy storage that you can see either through hydrogen or batteries or through pumped hydro, redox flow batteries. These are all important part of the puzzle. And energy is not enough. We also will have to do something about carbon, including most likely about negative emissions. How do we take carbon out? And then international cooperation. This is really, we share the same planet. We have to work together across the world to meet the goals of the Paris Climate. And for this generation, there's never been a more important problem to work on. There's never been a more important time to work on. So on that note, I think I'm going to stop here. And day 4 tomorrow will be batteries, and then day 6 will be thinking a little bit beyond conventional batteries to what comes after, and then also thinking a little bit about carbon on that day. So I'm going to stop here. Thank you again, and I'm happy to take any questions.
Thank you, Professor Sarbajit. Now I request Dr. Ufana Riaz, you may please ask questions on behalf of the participants. Dr. Ufana Riaz.
Good morning to all of you, and it was a very informative lecture, and again an exhaustive representation of all the data that is required, for understanding the need for solar energy and renewable resources. It contained a lot of information. So coming back to the question and answer session, so the first question is that does these alternative resources of energy production lead to the death of birds or warm-blooded vertebrates?
That's a really good question. So this is a really good question that how do we address our place on this earth, right? And how do we work on this sustainably? So one of the biggest challenges with wind energy has been, bird kills, and there's work going on to make sure that birds avoid windmills, but it has been a consequence. And then with solar power, there's a lot of work done on using concentrated solar and such, which also has a very adverse effect in certain regions. So I think as time goes by, we're going to have to be much more deliberate and intentional in mitigating the effect of these impact of these issues on the climate. I think if you were to ask me, certainly these issues of birds and such getting killed by solar installations or wind installations are bad. But I think what is more serious and that doesn't get as much publicity is all of the critical materials that are required for wind and solar. For example, rare earths that go into the motors of wind. There's a lot of samarium. There's a lot of neodymium that is required. Batteries, of course, require a lot of cobalt, and the environmental implications of mining some of these critical materials that are required for green energy can be really immense. And I think this is something that I will focus on in my last lecture, is addressing these materials criticality need and just generally sustainability. I'm going to mostly focus on the buildings industry, but thinking about sustainability. So really the bigger question, I think, from the perspective of the environment is that unlike the world we live in, which we know and understand, lots of carbon getting used and burned, this new world that is coming uses a lot of different minerals, lots of different rare, difficult to source materials that are often extracted at a very high environmental price. So while it sounds great that we're using green energy, we're going to have to be very careful about the sustainability of these resources and what is the ultimate price that we pay for using these minerals.
The other question is, which single technology could provide our society with a seamless transition to cheap, safe, and carbon-free energy?
Okay, that's a good question. So, if you ask a lot of colleagues, if one day we could get nuclear fusion to work, and I'm not optimistic. I haven't seen a lot of success there, but that could be the magic bullet that gets us there. So certainly there's need for research, but nuclear fusion is the sort of stuff that requires a massive project. We have one, that where India is also part of this ITER project in the EU. That would be, but more realistically, there is no way out apart from solar, right? Just because I don't see nuclear taking off. There's just no appetite for nuclear. So really, solar is the one solution that is really going to lead the entire energy revolution. But of course, if you're going to rely so extensively on solar, we will have to have very good energy storage solutions coupled with it. So not just photovoltaics, but also photocatalysis and then coupled, to batteries and to pumped hydro and all of that.
Again, another question on solar energy, that why aren't we focusing technology for commercial domestic level on solar energy, which is easily available? As we know, there's global warming going up. So why isn't there a force, applicable for focusing, hardly on this solar energy?
You're right. So like I showed you, hopefully, the challenge is quite a difficult one, right? So if you think about this, here's where we are. So here's where we need to be, right? We need to have things, or really here's where we need to be, right? Where we have very high efficiency performance, so we can reduce the land use requirements, right? And also low cost, so we can cover large areas and get lots of energy out of it, right? But the challenge with existing solar is the efficiency is low, which means that you're going to need a lot of land. As you know, in India, land is not easy to get, right? And large amounts of land. and so the efficiency is low. So you need a lot of land, and then you also have to worry about the cost. This is also a major challenge. So until we go from here to here, remains a challenge. I think people are doing the best they can with what they have now, but ultimately for much more widespread adoptions, A, we're going to need to be here, and B, we're going to have to address this issue here of the fact that solar is the absolute worst in terms of capacity factors. Okay, so solar is our only alternative because there's no real sustainable options out there, but we're also going to have to do something about these numbers here, and well, having storage linked up to it and having more efficiency, having lower costs. And again, a lot of these, at least the efficiency, is a scientific challenge. How do you overcome the Shockley-Kaiser limit? How do you do multi-exciton generation? How do you essentially work on all of these challenges on hot carrier extraction? So these are all issues that I think will be ultimately solved by science.
The next question is from the electrochemistry perspective, that where does the electrochemistry play a role in power generation? Do you have any statistics to see the growth of it?
So electrochemistry is, of course, everywhere, right? So if you wait for my lecture tomorrow, we'll talk about batteries, which is, of course, at the heart of this. We talked, my first lecture was about photocatalysis hydrogen generation. Now, clean hydrogen generation, I mean, there's lots of hydrogen used, but mostly coming from methane steam reformation, not electrocatalytic hydrogen generation. Clean hydrogen generation is still extremely lacking. It's not a major contributor yet in the world, not even at the level of 1% in terms of the global energy scenario, primarily because we don't have good catalysts, because the efficiency of the catalyst is low, which requires these large stacks, right? So lots of work to be done, but clearly electrochemistry will be key. And the other thing I want to mention, and this is my lecture, a couple of days from now, is we were simultaneously discussing not just energy storage in the form of batteries, but also what are we going to do about carbon? And I think carbon dioxide reduction is a huge frontier for electrochemistry. So not just doing hydrogen evolution or solar fuel production, but how do we do solar carbon dioxide reduction? I think that there's lots of opportunities here that we for electrochemistry.
The next question is, can we recycle silicon solar cells?
Yeah, so there's a lot of work being done, and of course, I mean, it's a great idea. I mean, it's a great thing that has to happen, and there's a lot of work being done here. As you saw, one of the biggest costs of solar cells is from the fact that we need 99.9999%, right? So if you've got a good silicon solar cell that's already very pure, processing that's going to be much easier than trying to make silicon from sand, right? So this is as we silicon solar cells are still relatively new, right? So there's not a lot of stuff yet, but as this comes online, I do think this is going to play a big role in dropping the cost. So we talked about how, so I think as recycling becomes a major part of this, we'll drop costs. We'll also drop the carbon costs associated with production of solar panels, which will also be great.
The next question is also related to silicon. It is that which materials are best to be coated on crystalline silicon to improve its efficiency in solar cells?
Okay. So I think maybe what you're asking about is tandem cells. So where you've got multiple materials doing this. Okay, and it really depends on what you're trying to do, and you might be trying to capture some very sort of high wavelength light using a band gap that is large, or you might be looking to capture some near infrared light. So there's all sorts of hybrid options there using other semiconductors, right? All the way from something like lead sulfide, if you want a small band gap, to other much larger band gap materials than silicon. So, but a tandem cell will usually have, 3 or more semiconductors just lined up. Cat telluride is another option, right? Which will be just all lined up to most effectively match the solar spectrum.
The next question is based on prediction. How long will it take to achieve the alternate form of renewable energy source that could fully energize the entire world so that we can get rid of toxic form of energy generation?
Yeah, that's a really good question. So I think the challenge is that even the most optimistic predictions, right, have renewable energy generation, like you can see here. And there's different scenarios, but this is perhaps the most optimistic number I've seen. As you can see, this is still a low number, 50%, right, by 2050. So we're going to need a much greater acceleration of adoption of renewable energy to answer your question. To fully energize the planet, will need a much higher pace. But at our current pace, we'll have to probably go up to 2075 or 2080, perhaps not in our lifetimes even, before we will have, full renewables. And part of this, of course, is political too, right? Is what are the policies? What is the global technology transfer that happens, technology sharing that happens that facilitates this?
The next question is based on power plants. Are hydrogen burning power plants feasible in the future?
Oh yeah, sure. I think so. This is something that is taking increasing. There's already a lot of interest in things like hydrogen co-production with all sorts of other industrial processes, and I think one can very easily envision hydrogen co-production also being used for hydrogen generation on site, and part of hydrogen power plants, right, is we can move away from this idea of having a massive coal power plant that supplies the whole city into the idea of much smaller plants that are based on microgrids, right, that will supply particular areas. So we don't have to have a massive hydrogen power plant. We could have electrolyzers and have them be part of a grid, which also includes solar, which also includes other sorts of energy generation.
Next question is based on lithium-ion batteries. The consideration of lithium-ion batteries. Are they good choices for electron transportation sector or any other sector?
Well, they are currently the leading choice for, they're overwhelmingly a winner in consumer electronics. So that battle has been settled, right? They are currently the dominant choice for electromobility across, and they didn't always used to be. Even perhaps 8 years ago, there were some questions, but right now they are completely eclipsing everything else. For grid level storage, they're probably not going to be the only choice. There are certainly better choices in terms of redox flow batteries, especially for longer term storage and other sorts of non-lithium options that are coming in. And I will dive deeper into this in my next 2 lectures as to where lithium-ion makes sense and where it doesn't. And I think the short answer to your question is it's not going to be a winner takes all. We're going to need a vast range of energy storage technologies, hydrogen, batteries, that will all fulfill different roles in this. Some more for grid storage, some for local microgrids, some for electromobility. So we're going to need a diversity of storage options in the future.
The next question is that, don't you think we are in a hurry for renewable solar energy, as we would be compromising with the environment and generating a lot of e-waste?
Sure. Well, I mean, so it's an interesting question. The alternatives are not very good either, right? So we have to. But the thing with going to solar energy, this is something that perhaps is a little bit underappreciated. The more our grid becomes electrified and not reliant on coal, the more the carbon costs of solar panels will go down, right? So when you talk about e-waste and the carbon costs of generating making a silicon solar panel, it's because our grid today is pretty dirty and it's powered by coal. 15 years from now, if we really are at 50% of it is solar, then the carbon cost associated with manufacturing a solar panel will also go down. But fundamentally, your question is important. Is how do we deal with waste? And this is a whole other question. We are going to have to move towards a more circular economy and not really treating anything as waste, but this idea that my colleagues who do life cycle assessment like to call, cradle to cradle, not cradle to grave, but cradle to cradle, where you're constantly using waste in a circular economy.
The next question is also related to the solar panel, that how important is the shape of the solar panel in designing solar power based units?
Yeah, there's a lot of research on this, and a lot of this has to do with solar tracking. What angle are they pointing at? Some of it, there's some effort on something I discussed, the idea of concentrated solar power and using particularly shaped collectors to effectively collect the solar power. So yeah, there's a lot of great research on here. Geometry is an important thing, and process optimization is an important thing. So there's a lot of engineering that has to be done, has been done well to get the shapes of solar collectors to be optimal given the angle of the sun in a certain area.
Okay, so the last question is, why is it required to separate electrons and holes if the electric current at the depletion zone does this for us?
Well, so you're going to, maybe I don't fully understand the question, but you're going to have to, ultimately flow the electrons through an external circuit, right, to generate power, right, to generate a current. So essentially, at the depletion zone, you're absorbing light and you're generating electron-hole pairs, but that you need to separate the electron-hole pairs and have the electron flow through the external circuit. So that's sort of why you need to do this in a here in this picture, for instance, here, right? You have to flow the electron out through an external load, and only then do you generate an external current that gives you, power generation. That makes sense.
There's another question that has come up. Is supercapacitor good choice for energy storage as compared to electrochemical energy storage?
That's a very, very good question. I mean, supercapacitor has a role. I would say a limited role. Again, supercapacitor research has been going, they've been really, really increasing how much energy density, how much total energy density they have. But really the role of supercapacitors conventionally has been for something that where you can store a bunch of energy and get it back in very short order, right? But not to do long-term storage. So there's not a lot of energy you can store, but you can get it back very quickly. Okay, so that's the role of supercapacitors. And this is not entirely true anymore. People are designing high energy capacitors that will go into kilowatts and tens of kilowatts. So this is true, but still much more the purpose of a supercapacitor is in this power quality regime, not really bulk power management, not really load leveling, but essentially saying, okay, I have a fluctuation in my grid, my high energy supercapacitor will help me balance this out, right? And this is going to be inevitable as we move to intermittent sources like wind and solar. There is a real risk of deterioration of power quality. So we're going to have some balances in place and some ways to buffer that. And supercapacitors will have a role, but much more short term than anything else. So there's really no alternative to ultimately to batteries.
So we've taken up all the questions now. I think I should now close the question answer session, and I would like to thank you for such an informative and insightful lecture based on energy and consumption of energy, starting from the consumption need for the consumption and then relating it to the need for developing sustainable resources, the utilization of those resources, and how we could actually ponder over to this problem and try to solve this at a mass scale. And the lecture was insightful in the terms of the statistics that you have represented, and I could see the participants requesting for your presentation, and they were so motivated by the stats and by the information that you have shared. I sincerely thank you for sparing your valuable time. It's late out there, I mean, in the USA, and you've really been, I mean, sincere towards answering all the questions and exhaustively giving a wonderful presentation to all the participants. I'm sure everyone has enjoyed it, and I thank you for your participation and sharing such a knowledgeable information to all the participants.
Thank you very much, Dr. Riaz, for your generous comments, and I hope to see you all tomorrow. Thank you.
Thank you so much.
Thank you.